When a massive star exhausts its nuclear fuel, its core can no longer support its own weight. The resulting collapse compacts the star's entire mass into a region so small that its gravity violently warps the local fabric of spacetime. This creates a singularity, a point of near infinite density, surrounded by the event horizon. Once an object crosses this boundary, the laws of physics dictate a one-way trajectory with no possibility of escape. We see the evidence of these invisible traps by tracking the objects surrounding them. At the center of our galaxy, stars like S14 and S2 follow precise elliptical orbits around a central point that appears completely empty, yet possesses the mass of 4 million suns. Radio telescopes have now captured the actual shadow of these objects. This image of the M87 supermassive black hole shows a ring of superheated gas circling the event horizon, confirming that these regions of no return are a physical reality. For decades, this evidence led to a singular conclusion. Black holes were cosmic graves, where matter and light were permanently erased from the universe. In 1974, Stephen Hawking introduced a discovery that challenged this idea of permanent burial. Using quantum field theory, Hawking showed that black holes are not perfectly black. They slowly leak energy in the form of radiation. This slow evaporation means that over trillions of years, a black hole will eventually shrivel and disappear completely. This creates the information paradox. If a black hole evaporates away, the physical record of everything it ever swallowed is seemingly deleted. This breaks the foundational laws of quantum mechanics, which state information can never be destroyed. If the universe is to remain logically consistent, the matter trapped inside must have a physical path to re-emerge into the cosmos. The search for that path leads back to 1916 and Karl Schwarzschild, who produced the first exact solutions to Einstein's equations of general relativity. General relativity is inherently time-symmetric. The foundational equations describing gravity work exactly the same way whether time flows forward or backward. If you take the mathematics of a collapsing black hole and reverse the direction of time, the result is a perfect mathematical twin, a white hole. A white hole possesses the inverse properties of its sibling. It is a region with an event horizon of no entry, an object that can only push matter and energy out, never allowing anything to fall in. Historically, scientists dismissed white holes as a mathematical curiosity. They argued that a massive eruption of matter from a singularity would look like an egg unscrambling itself, a violation of the law that the universe must get more disordered over time. Without a clear physical process to create such an object, the white hole remained an ignored quirk of the math for nearly a century. That changed with the development of loop quantum gravity, a theory championed by physicists like Carlo Rovelli. This framework suggests that space is not an infinitely smooth void, but is instead composed of discrete, quantized building blocks. Under this theory, matter inside a black hole cannot collapse into an infinitely small point. Once it reaches the Planck scale, the absolute minimum size allowed by space, the compression stops and triggers a violent rebound. At this level of density, the singularity undergoes a process called quantum tunneling. The intense gravitational energy causes the entire system to turn inside out. This artist's rendering shows that transition. As the black hole funnel on the top reaches its limit, it connects to a white hole funnel opening into the future. These stable, microscopic white holes provide the mechanism to spit the trapped information back into the universe, potentially resolving the crisis Hawking discovered. If black holes are constantly bouncing and becoming white holes, it raises an obvious question: why haven't we ever seen one? The delay is caused by extreme time dilation. In general relativity, time passes slower the closer you are to a massive gravitational source. For the matter falling inside the hole, the bounce happens in a few seconds. But for an outside observer, that same few seconds is stretched across trillions of years. At 13.8 billion years old, our universe is simply too young for this process to have completed. Most black holes won't reach their white hole phase for trillions of times the current age of the cosmos. This transition forces a radical rethink of how space and time function at their limits. In this model, the matter falling into a black hole enters a state of extreme compression that is, by definition, temporary. These regions function as cosmic cocoons rather than permanent ends. Applied to the largest possible scale, a white hole represents a massive, sudden explosion of matter and spacetime expanding rapidly outward from a single point. This outward trajectory is a mathematical mirror of the Big Bang, the event where our entire observable universe emerged from a similarly dense state. By tracing the mechanics of the theoretical white hole, we find a potential explanation not just for the death of stars, but for the very origin of our own universe.